This is section 2.5, part C, still talking about inverse functions. We're now going to talk about trying to find the equation of an inverse function. And once again, we're going to go back to the idea that in an inverse, the x's and the y's trade roles. So, if I start with my function, I'm going to begin by just rewriting it. If it's in function notation, I'm going to rewrite it as y equals. And then right here is the step that makes it an inverse. I'm going to literally swap the x's and the y's. If I solve this new equation for y, I'll be able to have the inverse function, and I'll simply plug in my inverse notation. So let's start in the first example with the given function, looking for an equation for the inverse. I'll begin by rewriting this as y equals. And while I do that, let me also go ahead and simplify that function a little bit. That would be 2x plus 6 plus 1. Or in other words, y equals 2x plus 7. All right, right here's the point that we're going to make it an inverse. I'm going to switch the x's and the y's. That equation is an equation for the inverse, but to write it using inverse function notation, it would need to be solved for y. So I'm going to do that. I'll subtract the 7, and then divide by the 2. And there's really nothing wrong with that fractional notation. If you want to, though, of course, you could split it up and say that would be 1/2 x minus 7/2 equals y. Because that's now the inverse function, instead of writing it as y equals, I could write in f inverse of x equals 1/2 x minus 7/2. And there's my inverse function. All right, let's try that one more time. This time my original function is 4 times the cubed root of x minus 2. I want an equation for the inverse. So again, I'll start by just rewriting it in the y equals form. And then right away, I'm going to make it an equation for the inverse by swapping the x's and the y's. This is now the inverse. I can't yet write it in inverse function notation, though. In order to do that, I have to solve for the y. So I'm going to add the 2. And then we'll divide by the 4. So I have 1/4 x plus 2/4, which is really just 1/2. And then finally, to get y by itself, I would have to cube both sides. So cubing the cubed root just leaves me y on this side. And I'm going to have to leave this one the way it is. Remember, I can't apply the exponent over a sum. If I really wanted to multiply that out, I would have to write it out 1/4 x plus 1/2 times itself 3 times. And I'd have a lot of FOIL or distributive laws to do to simplify. So I think it's much simpler to simply leave it in that form. And the last thing I'm going to do is write it with the inverse notation. F inverse of x equals 1/4 x plus 1/2 raised to the 3rd power. All right, so those are ways to find algebraic expressions for inverse functions. I also want to talk a little bit about the algebraic relationship between a function and its inverse. The question we want to ask is, what happens when you take the composition of a function with its inverse? So remember compositions from our last section, 2.4. In one of the examples that we just finished, we found that the inverse of this function was 1/2 x minus 7/2. This is the first example on the previous page. I'd like to go ahead and let's fill in the chart using this function and this inverse. So I'm going to start with a function. Using these inputs, 1, 2, and 3, let's plug them into f and find the outputs. It's up to you. If you'd like to go ahead and do it with a table, you certainly can. I don't have that many points to plug in, so it might not be that hard to do either mentally or just with a calculator. But since you can't see inside my head, I'm just going to go ahead and type them in. Plugging in 1. We're going to get 9. Plugging in 2. We get 11. And plugging in 3, we get 13. So we're going to get 9, 11, and 13 as the outputs for f. All right, I'm now going to take these outputs for f and plug them in as inputs for f inverse. So they're the same numbers. I'm just going to rewrite them. Right? Essentially, these y values have now become x values. We've traded roles to make them inputs for the inverse function. And I'm going to plug the 9, 11, and 13 into my inverse function. Once again, these aren't too bad to do in your head, but since you can't see inside my head, I'll plug them in the calculator so we're all on the same page here. If I plug in 9, I would have 1/2 times 9 minus 7/2 is 1. Plugging in 11, 1/2 times 11 minus 7/2 is 2. And finally plugging in 13 gives me 3. I'm sure you're not surprised to notice that by the time I've taken my inputs, done f, and then done f inverse, I get the exact same inputs back again, don't I? And again, that's not real surprising, since we understand how inverse functions work. So, what we notice is if I take an x value, oops, let me try that again, value, there we go. I do f, and then I do f inverse. I get the same value back again. And of course, that's because these do and undo. So it's very reasonable that I would get back what I started with. Remember back in 2.4 what we called it when we applied two functions, one after the other? We always call that a composition, right? So what I've really done in this table is I've really created the composition of f with f inverse. F of f inverse of x. We looked at it numerically up here, but could we do it using the functions themselves, the algebraic expressions for the functions, and see what happens? I think we can. If I would like to find f composed with f inverse of x, That would be f of f inverse of x, or f of 1/2 x minus 7/2. And if I go ahead and plug the 1/2 x minus 7/2 in for that x right there, I'll have 2 times 1/2 x minus 7/2 plus 3 plus 1. Let's simplify that. If I go ahead and I distribute that 2, I'm going to get 2 times 1/2 x, which would just be 1x, minus 2 times 7/2 would be 7, plus 2 times 3 is 6, plus 1, which gives me x. And then notice negative 7 and positive 7 give me 0, so I really just have x again. We've shown once again that whatever x we put in, by the time we do both the function and the inverse, we're going to get that same x back out again. Anytime you have a function and its inverse, their composition should always just give you the x value back again. Let's take a look at that with one more example. Here's a formal statement of what we just saw. We'll conclude that the composition of f with f inverse is just x. And it actually works both ways. The composition with f inverse and f is also x. We're going to verify those statements for the other function that we had. This again is one that we did just a little bit ago when we looked at 4 times the cube root of x minus 2. We found that inverse function. So I'm just going to copy that over right here. And let's verify that the compositions of the function with its inverse and the inverse with the function give us x both times. I'll start with f of f inverse of x. So that would be f of this f inverse of x and if I plug that in to the function itself, I'll have 4 times the cubed root of 1/4 x plus 1/2 cubed minus 2. The cube and the cube root basically just cancel one another out. So I have 4 times 1/4 x plus 1/2 minus 2. And then distributing that 4. 4 times a fourth just makes that 1x. Plus 4 times 1/2 would be 2. And then I've got the minus 2. And there it is. Whatever x I put in, I'm just going to get x back out. Those are true inverse functions. Let's try it the other way. Let's take f inverse composed with f of x, which would be f inverse of f itself, 4 cube root of x minus 2. So I'm going to plug this in for the x in f inverse. So I'm going to have 1/4 in place of that x, I'm going to put 4 times the cubed root of x minus 2 plus 1/2 all to the third power. All right, that looks like kind of a mess right now, so we're hoping that's going to simplify nicely, and I think we're going to get lucky here. Inside my parentheses, I'm going to start by distributing the 1/4 to both terms. So 1/4 times 4 is just going to make that 1 times the cube root of x, minus 1/4 times 2, 2/4 or 1/2. Then I have a plus 1/2 out here, all raised to the third power. Of course, inside my parentheses, positive 1/2 and negative 1/2 make 0. So I just have the cube root of x to the third power. And once again, the cube root and the cube essentially cancel one another out. They're really inverses. And I get x. So whichever way I choose to investigate the composition, when I plug in x and I do both f and f inverse in composition, I end up with the same x back again. All right, we'll take a look at a couple of examples of modeling functions applications in the last video for this section.